All right, thank you. Yeah, so I think thanks for the invite to come and talk. I'll talk a little bit about some of the technology that we're developing on microscale selective layer sintering, mostly for 3D sort of bump fabrication sorts of technologies. So this has really been driven by kind of the idea recently that we're moving away from kind of these large scale monolithic pieces of silicon to kind of a chiplet economy where we have high mix, low volume sorts of applications. And we want to be able to kind of rapidly be able to swap out different chiplets in kind of a structure in order to make development times lower, but also, as you get to finer resolutions on some of these chips, yields go down as you make big ones. So, and you can increase functionality by having multiple types of chiplets kind of in a package. And so that's really kind of the thing that we've been looking at. And what you see generally is if you make kind of a interconnect structure like this AMD processor, right? You have all these layers of interconnects, and then at the top you have kind of your bump structure on top. Generally, to make that bump structure, you're going to have one set of mask designs. That's a static mask design. You're going to do your patterning. You're going to fill that with a seam material. You're going to electroplate up to kind of build your pumps, your bumps on top. And then every time you want to make a change that design layout, you need to make a new mask, right? And so the idea that we're trying to work on is, if we can build these bumps without having to create kind of new masks every time that we want to build a new product, and do that kind of at industrial kind of resolution, so sub 10 micron sort of pillar diameters to kind of get these for kind of our custom applications. And so we've been doing a lot of work on kind of how do we scale kind of this sort of bump format fabrication in an additive sort of a process. And so really going from kind of what we can make with like a solder ball jet or something like that, where typically 50 to 100 microns sort of ranges down below 10 microns are some of the features that we're trying to make in some of these pillar arrays that people are building for semiconductor packaging sort of applications. And so the first step in that was we kind of looked at what exists out there in terms of types of additive manufacturing systems that are common in practice and what they can do. I think for this application space, there are kind of 3 metrics we really wanted to be able to hit. We want to be able to build sub-micron or micron scale features. We really like to build kind of true 3 parts. So, 2.5D is great, but the future of this is really building kind of 3D sort of interconnect structures on top of these chips for advanced flexibility. And the throughput really needs to be high for these kind of semiconductor applications, in the 1 to 2 millimeter cube per hour sorts of fabrication ranges. And there aren't a whole lot of processes out there that can hit those sorts of targets. So what we developed was what we call a microscale selective sintering process, which I'll talk about kind of how that works in a minute. But if you're familiar at all kind of with additive manufacturing, kind of our standard selective layer sintering process or direct laser melting process, basically what you do is you take a powder of particles, usually metal particles. You'll spread them on a surface. You'll scan a laser kind of across that surface to locally melt those particles. You'll lay down another layer of particles on top and kind of repeat that process over and over and over again until you get kind of your 3D part. And so this is great for building big things. There are big challenges here going to small things. Typically the laser spot size on a machine like this is in the hundreds of microns. The powders typically have diameters on the 10 to 50 micron size scale. You're generating a lot of heat, so the heat affected zones around kind of the small spots you want to pattern are quite large. And so what we ended up developing was a similar kind of concept, but a microscale sort of printing process. The big difference is here we use nanoparticle links as opposed to macroscale particles. So our particle sizes are sub 100 nanometer particles. That leads to some obviously spreading challenges. You can't do this as a powder anymore. Nanoparticles like to stick together when they're in powder form, so it has to be spread kind of as in ink. So what we end up doing is basically spreading a layer as an ink. We dry out that layer of ink. We do our patterning. We spread out another layer of ink, kind of dry that layer, and repeat that process over and over and over to build our 3D structure. The other challenge is we need to pattern small features. And so a single sort of spot laser scanned around doesn't really work anymore, kind of at the throughput that we want to go to. So we incorporated kind of a digital micromirror array into this system. We basically take a laser, focus it off that digital micromirror array. Each one of those pixels in that micromirror array gets focused down to about a 1 micron spot size. So we're patterning about 2 million 1 microns